Okay, hi everyone. My name is Min. I'm one of the lecturers in SOC and one of the faculty here. I'm an associate professor and I do research in web, information retrieval, and natural language processing. And we are experimenting with a new format for a lab rotation course, which you have kindly subscribed to. And this should really be a chance for us to get to know each other and to network and to learn the materials better together. So I'll go over that a little bit. Whoever is in charge of the session can decide whether they want to webcast or not. I'm pretty comfortable with it because I have to do it as part of my professional practice. So for that reason, I'll just go over what I have and then also give you an overview of how I want the course to run. Okay. So welcome. This is the first session of Deep Learning for NLP. This course is open to the public, so we welcome your participation in any way, shape, or form. Let me start with what this course is not. Okay, this course is actually, believe it or not supposed to be a lecture. I mean, that's sort of silly, right? Because this is actually a seminar course, which we ask students in the class to take turns, learn the materials on their own, and then, by virtue of knowing 1 week's material very well, we can present it in class, and everyone in the class benefits from that, and we can level up the community. So I think, can I have a show of hands who's actually officially enrolled for this course? One. I know I had at least one other person. 2, 3, 4, 5. Okay, so those of you who are actual CS postgraduate students in your first year, you've enrolled for this class, that's great. This is the course that was meant for you, but we've broadened it, as you can see, quite substantially to include other people as well. So hopefully you are one of these people here. I'm sorry, you can't really read that. So Xiaofang, are you here? Yes, okay. And Piao Piao, okay. And Nicholas, I saw earlier, and yeah, Kai Ning. Okay. So the 4 of you are part of this session where we have you study 1 or 2 of the week's lecture materials and prepare a presentation. Actually, you already have the slides. Socher has kindly prepared all the slides for the course. And then all you have to do is give the lecture. That's what you are doing to get the modular credits for this class. Now, we have so many people. I'm sure all of you are like, wait, I have a first-year graduate student. What am I doing lecturing, right? So we want to also give you the opportunity to work with other students in the room who are from industry, who might know the material better, who might not know the material at all, and join together to learn 1 week's worth of material to present. Okay? So as I said, I'm Min. I lead the wing group. There are a number of my students here. You'll also hear about them a little bit more. They're mostly sitting in this middle row over here, alumni as well as current students. And I'll have a little bit more to say about them, and they'll introduce themselves. Okay, let me go over a couple more house rules. Okay, so as I said, this is not a lecture-style course. This is the only part where I'm going to actually lecture is today, but mostly a seminar. I hope you guys will break in and ask questions. Really, we're trying to just level up and network the whole group as a whole. It's not a replacement for the Stanford course. So I know a couple of you were actually at Stanford and took this course. Is that right? So I know one person who did. So if you happen to have taken the materials from this course before, that's great. You can help with other people. But that course is a lot more intense, right? It includes programming assignments and a project. Now, most of you from outside, you're working adults. You don't have time to do that. So this is sort of like a stopgap replacement. You want to know a little bit about deep learning, or you want to know a little about NLP. This is one way that you can do that. Okay. So you're encouraged and welcome to try to do the programming assignments for deep learning. We'll open a Slack channel. So hopefully you are using Slack. I know a couple of you are somewhat active. If you're not using Slack very often, That's not surprising. It's actually hard to get notifications from Slack very much. Just try your best to keep pace, because we have people who are actually physically here, like all of you, but many people who couldn't make it, who still want to keep track of what's going on in the course. Then you might not have a choice. You have to watch this terrible webcast that I'm recording right now, as well as participate in Slack. Okay, so good luck with that. Okay, what this course is, I think really we're here as a community, right? We all want to know a little bit more about deep learning. What's the hype? How is it carried out? How difficult really is the math? Could I apply it without understanding the math? And so we want to have a chance to be introductory material at the graduate level. We should also know some math, matrix algebra, calculus, etc. We're going to tackle the materials together. So really, all of us in this room, we come to this course with very different expectations. Some of you are very good at math. You use all of the complexity of linear algebra every day, and some of us, we took it before. Okay, so we have all types. So if you get questions on Slack that you think are very easy to solve, it's because we're coming from all different levels, and so you shouldn't be afraid to ask a question that you think it might be fundamental knowledge to someone else, because chances are there are other people who have very little knowledge of the math, of the application of domain areas. Okay, so that's the idea behind this course, is just to put everyone together, mix it up a little, and then hope that something else comes out of it. There are some seats up at the front. There's at least a couple here if you want to move from the back. Okay, so the way I end this course, and it's really just an initial idea, I hope through Slack or through other channels we can come to a consensus of how it's best to serve this entire community, especially the 4 students who are officially registered for the course. What I think we can do is we're going to have 3 groups of people in this class every week, and these groups will rotate. Okay, we'll have one group to present the materials. So for example, I'll be presenting the materials from Socher's introductory lecture today. Okay, then we'll have another group who's seated to ask questions. Okay, I find that discussion in like these seminar lecture style classes don't work very well, right? Because you're just broadcasting and you don't want to interrupt the lecturer with your questions, right? But actually, it's very good to do that. So we'll have one group that's assigned just to look at the material and say, I don't understand that. This doesn't make sense. How did that equation come from this one, etc. All right. So your task is just to bug the presenters. Hey, what happened here? Okay. And the audience is, just general form, right? So the last group to listen, to take notes, to participate in Slack, whatever, so that we can learn about each other. Okay. So this course is, I think, really a chance to network too. I mean, I advertised it on Facebook in data analytics and another couple groups, and suddenly we got so many people interested. I didn't know there were so many people in Singapore interested in deep learning. So this is quite exciting to me. And this always happens to lecturers, so let me take care of that. Okay. So I will tell you a little bit about my research group, just to keep it short. And what I hope is that all of you from different companies will also speak to each other and share your stories about what you're doing. So we want to keep the presentation material limited to about an hour, so we have more chances to talk. Because I think this is what is going to level up our community as a whole, is when we don't sit next to our colleagues, we sit next to people we don't know, we exchange information about what problems we're challenged with, and then we can learn about how deep learning or NLP can solve those problems when it's not applicable. Okay? It's also a chance to present. I want to hear from all of you in industry and who are taking this course officially, what your background is, what interests you about deep learning or about NLP. Okay, and in these types of discussion, we want to make sure there's a level playing field, that no one hogs the floor, or everyone has a chance to speak. So we will do moderation for. Okay. Again, this course, as I said, even though there's about 70 people in this room, there's only 4 people officially taking this course. Those are our privileged few. Okay, so we have to make sure their needs for this course are satisfied. Now that just means that they have agreed that this time is free for them, and they are willing to hold this course to accommodate all of you from industry to come in after hours to to listen to this, okay? So session 1 is weeks 3 through 7. So I think you saw that here. Basically, we're going to go over the intro to NLP and deep learning, word vector representations, language models, softmax, single layer networks, neural network backpropagation for named entities, and then neural networks, and hopefully we get a chance to go through TensorFlow. Okay, that's for the first session. That will be Tuesday evenings from 6 to 8 p.m. So this time slot now. In session 2, earlier I said it would be on Thursday. It turns out at least two of our students out of the 4 that are registered for this course can't make it on Thursday. So they're going to have to switch it. We don't know exactly the time yet. They said they have 2 days, Monday or Friday too. So we're going to leave it all up to you guys. Okay, what timing is that? Most people don't want, right? But if you do, that's fine. I'll ruin mine with you, and we'll do it on Friday, okay? But possibly Monday evening instead, okay? As I said, we'll try to end early so we can have more discussion among all of us. The gantry at SOC's parking lot opens at 7:30. Who drove here? Anyone drive? Okay, so for those who drive, 7:30 is when the gate opens and you can get out for free. Otherwise, it's some crazy lunatic rate of like 8 cents per minute. Okay, so it's like working in the CBD. Okay, so if you have problems with the gantry, let me know. Otherwise, you can go whenever. So any questions so far? Okay, I wanted to share one other thing with you, is that in Slack, earlier we said there was a page, where was it? This one, which has the worksheet for how we're going to organize this course. So what I need all of you to do is to put your Slack handle down if you have one. If you don't have one, never mind. Just put down your name, okay? And so I know that the sheet's not quite editable, so I'll fix that later on this evening. And just write down where you're from, if you don't mind disclosing that, whether you're coming for this session or both sessions, or possibly the second half, which is weeks 8 through 13. And then which 2 sessions you are interested in preparing for. So probably what I'll do is this column here, the D column will be the one that you actually present, and this column here will be the one that you ask questions for. Okay, so you have to prepare 2 weeks. One, to go over the actual lecture slides that Socher has already presented, and try to explain, work out whatever you can, okay? And then the second week to ask questions, okay? That will be the format of the course, all right? Now, obviously, with so many people in the room, we have multiple presenters for the same. We're gonna try to figure out some way of structuring it. I'll work with presenters so that we can have maybe every couple of slides change a presenter so that one presenter can just note that material, or you can decide how else you want to structure that. Okay, and if you don't mind having your name advertised in lights on our webpage, let me know. I will add you as a guest name. Some people may not want their companies to know that they're taking a course. I don't know, so it's fine. If you don't mind, I can write your name here, and I can link to your personal webpage or your professional group's webpage, etc. And this will be a chance again for all of us to refer to each other. Oh, I remember this gentleman, this lady was taking this course. I want to meet up with them to see how that problem. And I've learned something else after this course that I think we can share and cooperate with. Okay, SG is smaller when we can network together to find good solutions to the common problems that we all face. Okay. So I'm going to spend only 5 minutes. Hopefully I can time this to make sure I don't waste time talking about my research group. So in NUS, we have a number of what we call international research centers. These are groups that we have professors here in SOC as well as professors in top-ranked foreign institutions worldwide where we collaborate with. So there are 5 old centers. This is in the process of changing. My lab collaborates with 2 of them. So there's one over here. This is called our Next Search Center. It's partnered with Tsinghua University, and we do user-generated content. So all the things that you post to Twitter, Facebook, Weibo, etc., we do a lot of analysis for. Now, this is not the only center that does this. Pretty much all of our centers overlap a little bit. So Anthony, standing in the back, is also doing some of this type of work as well. Terrence also in the back over there.
I'm here because some of the company that.
Okay, awesome. Thank you. Okay. Actually, a lot of different research centers out of the 5 that are here have overlaps with monitoring social media. On the other side, we also have the Chinese Singapore Institute of Digital Media, or CSIDM. This is a lab that's joint with the Chinese Academy of Sciences. And here we do natural language processing, especially for language learning. So the idea there is to help language mediation. Use NLP to help correct essays that are from students, to help people learn foreign languages. Okay, so my group is called the Wing Group. Why do we call that? Because it doesn't fit in any one domain. We do a mixture of different things. There are lots of other groups in our this is more information for the 4 of you. You're choosing other labs that are interested in this area. Of course, we should mention Huital's group, the NLP group. They do core NLP, more like part of speech tagging, all of the basic types of language processing technologies that you'll hear about in the Socher lecture coming up. Okay, Tat Seng, as I said, deals with social media content, and we have a machine learning group. The vision group is represented here by Terrence in the back in the blue shirt. So everyone. This is Terrence, our biometrics and vision folks. And we have an artificial intelligence lab, which is led by many different people. So my particular group is an applied group. Okay, so it's a little bit closer to industry in the sense that what we want to do is use NLP and IR as tools to help solve problems in the particular domains in other areas. So it could be social media, could be in education, it could be in digital libraries, which is a passion of mine. Okay, I'm just gonna, this is pretty much the last slide, some of the research topics that our students are doing. So Tao, I think Tao is here, she's in the green shirt. She's leaving for the US in the next couple of months for a postdoc. She has been working on image tweets. So when you tweet in Weibo, you tweet in Twitter, sometimes you include an image. What relation does that image have to the text? She's tackling that problem. Shang Nan is also here sitting next to Tao. He's a postdoc in the next group. He's been working on using comments in Web 2.0 items. So when you post a comment, other things like that, we can use them to mine information out of them. Not only is the information in the text hole, but the information about who that person is, time they made that comment, helps a lot in determining an item's importance. Okay, Mutu, who's also sitting in the back in the green shirt, he's been working on MOOCs, massive online open courses. There, the idea is that instructors have very little time to talk and engage the audience in the discussion forum, because generally there may be thousands or hundreds of thousands of students. They post so many messages, it's very hard for instructors to prioritize what things they want to intervene on. And actually, the easiest way of presenting the forum results, where you have the first item be the last, most recently updated, actually messes things up a lot. Instructors can do a lot more good by strategically intervening on discussions that have strategic benefit for the whole course. Kishaloi is also, I don't think he's here right now, but he's working on thread recommendation in healthcare forums. So if you think about consumer health, okay, lots of posts about what's going on in people's lives, about what sicknesses they're having. And what we're looking at is try to recommend which threads or which discussion forums are of particular interest to a user. Interestingly there, the fact is that users come to health forums for different reasons, okay? You might think consumer health, oh, I want to find information about a particular symptom or disease. But that's not the only reason why people go there. People go there to get emotional support, to find out more about medications, okay? So there are a lot of other social reasons that are interlinked behind recommending threads, and we have to model the user well to do that. Okay, Chachan is also in the front in the orange shirt here. He was looking at discourse, structure in forums. Say when you post a discussion, maybe you've misplaced it in the wrong place. He's working on technology to help automatically moderate and move the discussion to the right location. So, you know, it's messy. Sometimes you post in the wrong place. You really meant to post somewhere else or cross-post it. His technology can help you. Wen Chang, I think is, I don't see him here, but he's working on implicit discourse relation identification. So that just means looking at clauses in text and trying to understand the relationship between it. If you know a little bit about NLP, NLP basically has the problem. For the last 40 years or so, we think of the sentence as the problem. Okay, so I have a sequence of words. It represents a sentence. Okay, and I'm going to do something with that sentence, like tag it or parse it, give it some structure. But when I go through multiple sentences and I need to understand the discourse, right? What's going on? How does one clause relate to another? Those are problems that only recently, within the last 5 years, are scientists tackling. Our group is actually leading some of the world's researchers by having a discourse parser that can work well on this. Okay, so we have a lot of other people here. I'll just mention one research staff since he's present. So Kaz is the first one on this list here. He works on recommender systems for digital libraries. So for example, you use Google Scholar to learn about deep learning or NLP. You might sign up for Google Alerts. So he's working on technology that implements that type of functionality. What you publish, what you've reviewed, what your past history is, we can give better recommendations to what you might like. Okay, so with that, I'm going to stop because I have a lot of other slides, but I'm not going to go through them. Rather than that, I think we'll go straight to the lecture material. Okay, any questions so far? Okay, so I hope to get more feedback. I mean, I'm really sorry it's such a terrible class that is, I mean, terribly large class that we can't really interact so much. So I hope we'll have a chance to discuss more. So please, please, please barge in, and I'll try to ask you some questions to prompt some discussion from you as we go along in the slides. So, okay, single page. No, I want full screen. Okay. So we're going to be talking about deep learning for NLP. And so the idea behind this, for this set of lecture slides, is basically just to do the introduction to NLP, deep learning, and their intersection. So who can tell me what this represents here? Can you guys see this in the back? Do you need me to turn off the front light? What is here? Yeah? Okay. Is that better? Yeah, a lot better. Okay, there's a sentence at the bottom, right? The first 15 minutes were dry, but by the end, really enjoyed the lecture. This is a sentiment problem, right? You see two words here, dry, with a label negative, and you see enjoy, which is with a plus, right? And so what we want to do here is, this is a sentiment analysis power. I want to find the polarity of this sentence, whether this is a good sentence or a bad sentence. So the first half of the sentence looks pretty dry, right? This doesn't look like it's a promising lecture. Let's see, how do I do that? Oops, that's not what I wanted. Sorry. Nope. Okay, good. Let's see whether that will work. Nope. Okay, never mind. So we have this part, which is a negative. And then over here, we have a positive. And I guess at this juncture, we have to decide which sentiment dominates, right? And so we're going to propagate this sentiment all the way to the root of the sentence. This is a structure. This is a tree, right? It's a binary tree. But basically, what this is representing is some type of parse of the sentence. Everyone know what a parse is? Basically, some structured representation of the sentence, right? So I have nodes, leaf nodes representing words. And I have intermediate nodes representing some value propagation. Okay, so we'll skip this. As I said, You can do the assignments in Python. You can try to take the projects and homework assignments you have. So if you want to do them, please reply or join the channel that will form on that so that we can link all of you who are interested in diving deeper down and participating in that. Okay, we're not going to obviously cover that. We don't have time to do that here. Okay, so natural language processing, what is it? So it's an old field, right? It's about AI. Probably famously, Turing, when he came up with the idea of AI and the Turing test, he thought NLP would be solved, one of the first problems that would be solved. I said, oh, language, that's easy, but playing chess, that's really hard, right? There's so many combinatorial search space of possibilities. But we already all know that, you know, most games that can be codified deterministically, they are solvable, right? We heard about deep learning for AlphaGo, right? And you can see some breakthroughs even in that combinatorially gigantic space, right? So the goal here is to be able for computers to process or understand natural language, right? And so that's why linguistics is in the picture too, right? We need to understand language, right? Or do we? There's a famous quote that's a sort of like an urban myth in the NLP field by Fred Jelinek. Does anyone know who Jelinek is? Anyone heard of him? Okay. So Fred Jelinek was a famed IBM T.J. Watson researcher in New Jersey. I've met him once when he was close to retirement age. And he was building one of the first machine translation systems. If you've done some NLP work, you've probably heard of the IBM Model 1, 2, 3, and 4. Okay, and he said quite early on that maybe linguistics wasn't so necessary. And then I think Fernando Pereira, now at Google, also echoed that sentiment. He says, every time I fire a linguist from my research team, my machine translation scores go up. Okay, so his machine translation fidelity got better the less linguistics he paid attention to. Why is that? We don't know, but we can hazard a guess that in certain areas we can use more and more data to make up for the fact that we don't have very strong intuitions about how language functions. If you talk to linguists, they'll give you lots of very complicated styles of grammar to try to account for all of the nuances of the human languages that we have. Okay, like dropping pronouns, inserting gaps, being able to cross dependencies, all of that. And actually, by using empirical data from language data, either type or speech data, which is oral and transcribed, we can learn a lot of those preferences statistically, probabilistically, that can model language very well. So there's a question about how much linguistics do we really need to do that? Okay, I think right now the benefits are there's a lot more ground to be leveraged through things like deep learning, through very complex models of learning that can still cover a lot more ground given the data that we have available. Especially if you're in a very large company like Google, which can aggregate petabytes, exabytes of data, then you have a very good chance of being able to create things like parsey, make parse face. Who knows what that is? It sounds like something out of McDonald's, right? Yeah. So parsey, make parse face is a Google piece of software that they open source and released. It's a parser for multiple languages. So if you're dealing with language data that looks like normal everyday news wire, like from the Straits Times or from the Wall Street Journal, chances parsey, make parse face, I know it's a really odd thing to say, will be able to help you parse those sentences fairly well. Okay, and it's not just for English, it's with a couple of different languages. Okay, so with that, we'll be able to compose parses like the ones that you saw on the first slide and be able to do tasks. Like everyone's now interested in chatbots. So can we do question answering with that? Can I represent the context and the background of the conversation, be able to answer questions in a dialogue system? But definitely, we find at the current stage of technology, that being able to fully understand and represent the meaning of languages, especially in non-restricted contexts. Okay, so if you're talking about in the domain of medicine, within the conversation of a doctor or a general practitioner, maybe there's some hope there that we can understand. Or if you're talking about, reporting Olympic news, maybe we're there. We can get some understanding of what you're saying and how that can form some type of semantic form. But generally, we're not anywhere close. Okay, so actually, because I'm not Richard Socher, I don't know why he circled those. So I'm just going to guess. Okay, these are the parts that have benefited the most from natural language processing and deep learning. So for example, in speech and text, there's two modalities of language. In speech, you have to obviously take the waveform that's produced and be able to do some type of a phonetic or phonological analysis. So for many years, from 1970s until about 2005 or so, the basic models for doing that were all based on hidden Markov models. Okay, it's a type of generative Bayesian model that you would run using the Viterbi algorithm to decode what was said by the speaker. Okay, from about 2010 onwards, there's been a big influx of deep learning that basically uses the very simple technology of the neural network or the perceptron that can do this much, much better. When they first reported the results there, they got an amazing error drop. So I think you'll see that later on in the slides. Okay. In text, you have to do things like if it wasn't born digitally, if it was an old newspaper, you would have this OCR it. No matter what type of language it is, even in English, you have to do tokenization. It means cut apart words into using white spaces to delimit words. But even in English, for example, you have words that are compound that have several different parts, like especially in medicine or pharmaceuticals. One long noun can have many components, right? And so it's actually better if you analyze those compound words and split them up. You can think about the case of German, right? So if you know German, basically some nouns are just like 50 characters long, and they carry the whole meaning of like traveling insurance salesman or something like that. Okay. In English, we have some words that you can break that are multiple words that you can put together to assemble a single word too. So, for example, mailman could be two words. They could be joined together. And so a lot of the tokenization issues come from that. Okay. So it's not only CJK languages, Chinese, Japanese, and Korean, that suffer from tokenization issues, right? Every language has these problems too. Okay. Morphological analysis. Does anyone know what morphological analysis means? No?
Analysis of morphology.
The analysis of morphology? Yeah, of course, that's right. What is morphology? Morph means something, right? So we're going to do morphological analysis on morphological analysis. How's that? So what's morphological broken down into, right? So there's this part morph, right? What does morph mean? Shape, form, right? So what possibly could we analyze shape and form in a language? The inflections, the shape of the word, exactly, right? So it means taking apart what the word looks like, cutting off the endings, understanding that, in at least English, we have a lot of words that come from French, Latin languages, which we can dissect, okay? Not so much for the Saxon languages, like the word bed. It's just the word bed. Sorry, you can't do much with it. Okay, but there are lots of other ones like internationalization. You can see the the nationalization part, and then we can understand the meaning of the word through morphological analysis. As one person said, we can remove the inflection, right? So if you have tenses, you have plurals, you have gender in French and Spanish, you can remove all of those to get the root form or dictionary form of a word, a lemma. Okay, and then we can do other things with that. So if I know the parts of speech of the words, then I can do the syntactic analysis to figure out whether that word in the sentence, let's say the word jump, refers to a noun or refers to a verb. Okay, so I can do that syntactic analysis. I can also try to parse the sentence, figure out what is the head of the sentence, the subject, which parts are the object or indirect object. And then also try to do semantic interpretation, right? perhaps take that some syntactic analysis and put it into what we call in NLP a logical form, right? Some type of representation of what that sentence means with variables as placeholders. So, for example, the word I could mean a person, the speaker in first person, and we would assign that thing to a variable that we could observe in the state of the room. So if I am speaking, I refers to this person, me, and I have a variable that concretely specifies that Min is talking. Okay, and as I said, eventually we want to get to this part in NLP where we look at discourse processing. This is still quite an elusive goal for many researchers, where what we want to do is compose all of these analyses, but not just for single clauses or single sentences, but put them together. Okay, so I'll give you an example of discourse processing. I have two sentences next to each other. I ate dinner with my friend. He paid for dinner. So what's the relationship between that? Was it a causal relationship? Was it a temporal relationship? He was late, so he had to pay, right? Or he was my student, so I had to pay. I don't know. Okay, so all those different types of signals that we take for granted as humans in processing, we need to get at as if we want to understand natural language, either through a chatbot, either through email processing, forum analysis, wherever you have natural language at stake. Okay, so there are so many NLP applications out there. I'm sure all of you can tell me more. So if you're from industry, can you give me an instance of why you're interested in the NLP? Just so that we can hear from you. And so I can drink some water. Someone from this side of the room? Come on, I know you guys were not in lecture for a long time, but you have your own group meetings, right? You want participants to speak up.
So in our campaign, we actually have a lot of comments entered by technicians. So we're trying to mine and get some knowledge out of those very experienced technicians on the comments that they entered when they fix the tool and so on.
Okay.
So when we use technician, right, we don't rely on the robots on how to use learning. They can actually use our so-called knowledge database to see what past things that we've done.
Okay, so there's a very good example. Let me repeat for those of you who couldn't hear. So maybe I have a knowledge base, a technical knowledge base entered with comments entered by technicians, right? I want to be able to mine or search that type of knowledge so that people coming in or third parties could use that knowledge base effectively, right? So there are lots of things that are related to that. So for example, that's a problem that hits with vocabulary, right? So you have technicians entering term A, but the layperson who's searching the customer's support doesn't know that that part is called part A. They call it, that thingamajiggy, okay? So then I have to be able to map those words to what the knowledge base says, right? I have a controlled vocabulary that's in place, right? That I have spent a lot of money buying and saying, you use this term when it means this term and never when it means anything else. Okay, and then you have people actually trying to use the system, have no idea about your controlled vocabulary, and they're trying to match that, right? That's a serious NLP problem too, okay? So NLP can definitely help with that, the synonymy matching. Someone else can give me a problem? So we heard from this side of the room. Thank you, miss. Sir?
Predictive analytics for legal research.
Predictive analytics for?
Legal research.
Legal research. Can you elaborate?
So like to come up with an application that can show for this particular kind of case what's the likelihood of an argument lying against the judge for this. So like you need to process all your text data from all the different cases that and how do you know what the relevant cases is.
Okay. So let me try to codify that in a slightly more formalistic manner. So the idea is I have a whole bunch of prior art that might be precedents for a case. So I can just number them 1 through n. And what I want to do is find the relevance of those proceedings to a particular issue, right? So I have a particular plaintiff or particular defendant, and I have all these documents. I need to rank them in some way, find the probability that they will be used by as prior evidence for a case. I mean, that's just one one instance of that. So I have to analyze the claims made by the technical arguments, right? Legal documents have a lot of structure. So we have to understand the dependencies between the arguments, right? And then using those dependencies, I have to map them to whether I think they agree with the document that I'm looking at, right? So I have, again, the vocabulary problem that we talked about earlier from this other lady, right? We have things that might not overlap. And again, legal has a lot of complications. So aside from the fact that the text might overlap, you might think, oh, the jurisdiction is different, so this precedent doesn't apply, etc. So it's much more than just an NLP problem, right? It's a legal problem. I don't know how else to say it. Okay, so definitely that's another one. Anyone else want to volunteer one other one?
Determining some problems that people generally tend to speak about, say in a forum or in a group.
Okay, so in a discussion forum, like in a large classroom or something like Slack, we might want to have a large group, have a discussion, and try to, let's say, cluster them together. So I want to bring like-minded discussions all together and make them aware of each other. Again, the vocabulary problem comes here, right? You might say online discussion forum, another person might say chatting or Fred or something like that. We want to maybe take all of the discussions and try to find, without any labels, some clusters of people or clusters of threads that represent the same type of information and pull them all together and say, hey, maybe you should get to know each other, or this seems like an important issue. Let's start a sub-forum for that. Okay? So those are just some of the applications that you guys are facing in industry. I hope to hear much more from all of you. But some of the other ones that you can see are very simple to complex, right? You have very simple things like spell checking, keyword search, and finding synonyms that can get very complex, but even spell checking is fairly simple. You have a language model that predicts which characters are misplaced, etc. You can think about extracting information from knowledge bases. If you think about the web itself as some type of unstructured knowledge base, you often want to mine facts from there, or facts from a knowledge base that's a little bit more structured, like Wikipedia. You might want to mine that. Extract maybe from Amazon, product prices, dates, locations, people, etc. Or classify things in other ways, like in education. Maybe you want to know the grade reading level, right? Whether to recommend this text to a P3 student or a P5 student for examination or not, right? And we saw an example of sentiment analysis on the top, right? So these are sort of like the middle tier, right? This is where we can do information extraction, and these are some applications of all of those things, right? Machine translation, everyone knows Google Translate. Spoken dialogue system like Siri or whatever other ones are out there. And complex question answering, right? Where we have session information that we take into account. So there's a lot of different things that you can do in industry. Again, some quite humorous examples of people using Google Translate to do translations, right? It says here, could not connect to translator service. This is obviously a hair shop, but because they just took the text verbatim and they printed a banner, that's how you find this hair shop now, right? You have to Google for could not connect to translation service hair cuttery, and then you'll end up there. Okay. In social media, there's cases like this. So I mentioned the name Anne Hathaway drive Berkshire's Hathaway stock. They're not related at all, but because they share the same name, the sentiment analysis keyword search does this, right? A lot of things that we do in social media, we look at keywords, keyword clouds, but we all know that's quite misconceived, right? Because single words, they don't carry enough signal. Even something like Hathaway could be ambiguous, right? So that's the state of a lot of our technology now, is that it's half-baked, right? It's not quite there. We think we have some smart things, and people pay for these things, but we all know in-house, I wouldn't touch that with a stick, but I will certainly sell it to you for $6 million. Okay, so NLP is hard for a lot of different reasons, right? So there's complexity in representing, learning, using linguistic knowledge, right? The hard one, I think, comes in all three of these, right? How do you represent the knowledge that you have, the state of the world as it exists when the system is interacting with you, right? Using both linguistic knowledge, even situational knowledge about who is speaking, the pragmatics of that. So for example, if I hear in an article, you know, the company reported losses today. Which company are we talking about, right? So I have to resolve that phrase and find the reference for that. So that depends on the contextual knowledge before, right? So this is a case of that. Jane hit June and then she fell. Who hit who? Well, Jane hit June, but who's she referring to, right? If you say, then she fell, right? She probably means who? June? June, because, yeah, maybe June fell because Jane hit her, or maybe Jane hit her, but June's an expert and threw her on the floor, then that would be Jane, right? Fell and ran, so it can be ambiguity. All right, here's another case of this. This is a standard lexical semantics, right? So I made her duck. Did I prepare a meal for her? Did I throw something at her? Not clear, right? So the situation between, from what came before that would help disambiguate what's going on there. Okay, so that's NLP. What about deep learning? So deep learning is the subfield of machine learning. I think everyone knows that. And the way that we've been working with machine learning for the past several decades is what a lot of people call feature engineering. Right? It means that a domain expert sits down with the data, thinks about the properties of that data, and says, okay, I think this piece of information would be useful if I were to try to figure out how to label that data, how to accomplish that task. Okay, so importantly, these are all human design features, right? They're the data is represented, codified by a person, right? So for example, in part of speech, we cut things up into chunks. Each chunk is called a morpheme or a lexeme or a word. Then we do some properties on that, like we find out whether they're plural, whether they're masculine, etc. And then we use those pieces of information, feed it into a machine learner by coming up with some representation as features, right? So features for finding named entities. Named entities are like locations or organization names. How would you find them in a newspaper? Can anyone tell me one feature that you would use for named entity, what they call named entity recognition? Capital letters, right? So IBM, Google, Apple, those are all capitalized. Great. What about in Chinese? Are they capitalized? There's no such thing as capitalization in Chinese, right? So how would you do it in Chinese, right? What other things can we think of in English that would signal a corporation name, for example? Sorry? Over here?
Private limited.
Private limited. Okay, we have suffixes that can indicate that there might be a company name, right? So we can iterate with that. We can say, okay, anything where I see private limited and something in the front, X in the front, that X is probably a company, right? And if I see that somewhere else, then I know it's a company, even though I didn't see it with that suffix later on. Okay, so for example, Terence Sim starts a company. There's a news report, Terence Sim Private Limited, and then later on, I see Terence Sim. Well, is it the company or is it the lecturer? I don't know. Okay, so those are all things in which we use our domain knowledge, our general knowledge to decide how to give the machine some features that are useful for classification. Okay, so we can think of all those as inputs, right? There are some features that we give. We can call them a vector of features, X, right? And so what we want to do is find some weights, some coefficients that we're going to multiply with these X values to come up with some separator or some classifier that can say things above this line, these are company names, things below this line, they are not. They're ordinary words, okay? So machine learning becomes just a way of optimizing those things. So you can see some of the basket of features that are used for what they call named entity recognition. The current word, the previous word, the next word, the part of speech tag, whether they're nouns or verbs, the current word shapes, that's that morphological analysis, say whether it's in capitalized or not, okay? Surrounding word shapes and things, and then basically we run some type of optimization procedure, you know, to be able to find the right coefficients to make that classification. Okay. So machine learning versus deep learning, right? So basically, in practice, what you want to do is use your domain-specific knowledge to describe the data to the computer, and then choose some type of learning algorithm using some data analytics package. Like if you use Python, you would use pandas and scikit-learn or something like that, and choose a learning algorithm, run it on a problem, and pop out comes a classifier that you can use on your data. Okay. Anyone have done those steps before in your daily practice? Okay. 1, 2, 3, 4. All the PhD students should have their hands up. Anyone from A-star, NCS, Micron? No? Okay. So this is what we typically do as a workflow. All right. We take the data, the language data, we come up with a way of representing it, features, and then we send that vector of features plus some information about whether that is the thing that you're looking for, not plus or minus. That's the output of the classifier. And we choose a learning algorithm to decide what to do with that. It could be, let's say, a decision tree or SVM or linear regression. Any of these types of things could be applied here. Okay. So deep learning is not like that. That is the old style of machine learning. Okay? Deep learning is basically saying, I don't need to do that. Okay? Arm me with enough data, arm me with enough CPUs, GPUs, and I might be able to do those human engineering steps for you. Okay? So there are several different parts of that, right? So the top part called representation learning. Okay? It's saying that I have a problem. I don't know exactly how to represent that data. Okay? But I have some raw input. Like, for example, I have an image rasterized and scanned from an X-ray. Okay? Or a fingerprint that I got from a fingerprint scanner. Or a piece of text that was scanned or downloaded from the web. Okay? That's the raw data. It's not the representation we want to feed as input to our learning problem, because usually it's too high dimensional. There's just too much information there for a learning algorithm to do something with. Okay? So representation learning is the part of deep learning that tries to automatically find good features for the representations of that. And next week, whoever does lecture 2 that talks about word embeddings is going to cover this in part. Okay? Deep learning algorithms are then trying to do this, right? They're attempts to learn multiple representations of a text or an input. So all of these are different layers. They represent that image, that text at different granularities of resolution. It's usually not very clear exactly what node does what. Okay, but at the end, we connect all of these outputs to a final node, which is supposed to make a classification. Oh, is this word part of a named entity? Is it a part of a company's name, or is it not? Or is this fingerprint somebody that I know and recognize, or is it not? Okay? So in Socher's course, he only focuses on the neural network type of deep learning, which is, I guess, very, very much highly represented in today's literature. Okay? And there's other things that they're not going to look at. So in particular, I've given you a little bit of background about the history of natural language processing and AI, but they're not going to look at this. We're just going to look at what's current and available for use. Okay? So again, as I have hopefully impressed upon you, the reason why people wanted to go this direction, because it's extremely costly from industry or even from PhD level research to try to engineer all of this domain knowledge. Right? You build a system, you want to figure out how to match vocabulary, how to overcome and decide which patterns are relevant, or decide which people are more similar to each other. And so I have to codify that. I have to come up with an algorithm or representation. So if I can learn that, then I just give all the data to the machine, and then somehow magically it will come up with representations of it. The difficult part is right now is it's not easy to explain what those representations are. So they're somehow encoded in the neural network, but we don't understand exactly what exactly is coded in them. Okay? So deep learning has this benefit that you can do away, hopefully, with enough data with certain types of domain knowledge. You're going to learn it from the data, and then also learn a classifier or other things that's going to help you accomplish your task. Okay? So as it says here, deep learning can learn unsupervised. That means we don't have to give it labels. I don't have to tell you Microsoft is a corporation name, Google is a corporation name, Minyan is a corporate person's name. Okay, classroom is an ordinary word. Okay. It can learn from this representation where I don't give it anything but the raw data, and it can also learn from supervised data where I give it that information. Okay. Any questions so far, Miss?
For the classification problem, is it still possible for the network to learn unsupervised?
Classification is usually supervised because you have to tell it what it is. Okay, when we do unsupervised, we typically think of this as clustering. So in the example that this sir gave, where I have a discussion forum and I have multiple people who may be talking about the same topic, I can try to cluster those together. Okay, so I give an example of, let's say, a 3-year-old looking at Singapore coins. Okay, so they have all these coins. They have dollar coins, 20-cent coins, 5-cent coins, 10-cent coins. We know what they are. We call them by those names, dollar coins. Well, the baby has no idea, but they can still group them together. I can say there's these coins that are heavy, they have 2 colors in them, and so this forms one cluster. I don't know the label for it. I don't know that they're called dollar coins, but I can cluster them together. So in a sense, it's classification, but it's classification without a label, right? And furthermore, many times when we do classification, we don't know actually how many groups there are. The coin example is sort of artificial because it's very clear cut, right? But you can imagine even that case is ambiguous. Let's say I cluster all the coins into ones that have a little bit of yellow in them, which is the 5-cent and the $1 coin, and all ones that are just metallic gray, right? That's another group. Okay, I can build clusters like that. I don't know whether that answers your question. Okay. Other questions? Okay, so those are the types of things that we typically have to think about. When we have a learning problem, we have to decide whether we're going to just give it the raw data and ask it to build some representation and some clustering from it, or whether we need to do supervision, which means that I have some indication of what that particular item means, right? What its label is. Okay. So here it says in 2006, 10 years ago, deep learning techniques started to outperform the traditional machine learning techniques where a domain expert had to sit down and codify what are the things. Okay, and so many times when we use deep learning, we'll see that it works very well on lots of data. In fact, in academic circles, us as researchers typically have very little data. So you in industry, we think of you as quite rich. Okay, you have lots of data, lots of samples, but perhaps not so much time or expertise. So that's why deep learning techniques are, I think, quite hot in industry. This is the promise of being able to do tasks without manual intervention with a lot of data. So you have all this chunk of data, you don't know what to do with it, well, throw it in the machine learner, hopefully something will come out, right? And you know, actually, deep learning techniques historically have been around since the mid-60s or 70s. This simple idea of the perceptron was codified in math back then, okay? But it's just that it was too expensive to run this at scale. So if you think about neural networks, in those days, if you talk to people in the 80s, they said neural networks are usually 1 layer or 2 layers, okay? Nowadays, when you think of deep learning, that's why they call it deep, right? Because there's multiple levels. Then you think 6, 7, 8, 9, 10 levels with very big levels, okay? So the fact is, in order to do that type of computation, you need a lot of throughput, okay? So when you have a GPU or something like that, that's multi-core, then you can enable all of these parallel computations. And that's where deep learning started to really fly, is when NVIDIA, ATI, all of these companies who built specialized processors called GPUs that could do lots of things in parallel, they started getting reused for what we call general purpose, graphics processing unit programming, GPUs. Okay, and so that became the driving reason why we can drive deep learning, because a lot of these types of computations are very, very simple computations, but they must be performed in parallel at the scale of billions or trillions of operations. Okay. So deep learning for speech. Again, the first result, this was the paper, all in 2010. So what they had are traditional features. This was the type of way they did it, first pass and then some adaptation. And here are the word error recognition rates, okay? So higher numbers are worse, okay? So if you ever remember using speech recognition technologies around 2010 or earlier, they were horrible, absolutely atrocious. You would say things and you get garbage out, okay? It's not that much better with deep learning, but it was quite a significant reduction. If you can see the bottom of the slide, 33% reduction. That means, you know, a third of the errors are gone. If you speak 3 sentences and there's only 1 error compared to speaking 2 sentences and an error, that's about the type of performance change that they got in this. So these are very standard data sets, very standard error recognition results. Okay, so the previous way people did it was to take the waveform and cut it up into phonemes. So here's the time sequence. You cut it up into phonemes, and you give all of these things into a hidden Markov model to try to decode into words. So there were several stages, okay? And they were codified as separate layers. In the deep learning approach, we just pull all of this together in a single neural network with multiple levels, multiple convolution neural networks. And then out pops the recognized sentence at the end, coupled with the language model. Okay, so this was the first time that deep learning was really applied at scale. Speech researchers couldn't believe it. They said, "Are you sure that's the right result? How can something from the 80s work, you know, at scale and give you such good results?" But it was validated, okay, time and time again. And we see now lots and lots of researchers actually only using deep technology in the area of speech. Okay. For computer vision, how many of you have vision applications? Deal with graphics? Great. Right. So here, deep learning helps a lot too, right? So most deep learning groups have focused on computer vision, okay, not in NLP. So there's one in 2012. These are trying to pull out these labels. Like this is flamingos, there are hawks in this picture, there are ruffled blouses, quails, etc. So to recognize the objects in the picture. So if you take the traditional approach, you would have to say, okay, there's something in the foreground. I can look at the texture of the image or blobs, etc., and do that. Okay, they didn't bother. They just said, I'm going to run a deep neural network. And each layer is going from, let's say, a local representation of what is going on in this patch, okay? And then trying to build up some information as we go up through the layers, right? So they're able to see, finally, from all of these parts, the same types of features that you might have manually needed to engineer, okay? Happening in the various levels of the neural network. Okay? So this course is about deep NLP, right? The idea is to combine both of these together, and it's had several big improvements, as you can see, in the levels that we talked about earlier, right? Speech, morphology, syntax, and semantics at all levels, and for the application areas that we've talked about too, especially machine translation, sentiment analysis, and question answering. So as I said, traditionally in NLP for speech, we would have to use linguistic analysis to come up with a representation. So this is the IPA alphabet, the International Phonetic Alphabet. All these symbols that no one knows how to pronounce except for linguists, right? So we would try to map sounds into recognizing specific phonemes. We can say that this is some type of alveolar stops. Like these are all the different alveolar stops that you can have with different ways of pronouncing the letters. flap or school plosive or etc. Okay, so we would actually have to try to classify into these specific bins, right? Say this is a D, or this is an N, this is an R. That's sound, right? But what we want to do is try to predict or learn these phonemes and represent them not as singular values. Let's say this is a D, but represent them as vectors. That's a range of possibilities of what a D should look like, depending on the range of speaker that we're talking about. Okay, representations again. The traditional idea going higher up. So once we have sounds represented as phonemes, we go one level up and we think of morphemes. Morphemes are the shapes of individual parts of the word, like anti or national or shun, right? All of those are morphemes in English, right? So in deep learning, again, we're going to keep the same representation. We're going to think of a morpheme as some type of vector representation, which is some type of a distribution of possible ways that could be envisioned. Okay? So for example, a neural network that combines two vectors into one vector. So I can combine two morphemes or two phonemes together to represent a new phoneme or a new morpheme. And then, so you have things like this, right? Where you can say, I have this vector representation. This is a vector. Okay, so there are individual units here. Okay, and I have the one for un that represents that, the one for fortunate as a stem. And when I add these together or combine them together using the neural network, I can get a new word, unfortunately. Right? So this works in English, but it could work across languages that don't even have this word. Right? We're basically representing the meaning of un, meaning something negative, and the meaning of fortunate, meaning, I guess, something propitious, right? And then combining them together by adding these two vectors together or concatenating them or whatever, okay? And then we can do the same thing. We can take this ly suffix, which in English changes it into adverbial form. Right? I have an adjective, I change it to an adverbial by adding ly at the end, right? So there's some other vector that represents this change. I pull them together and I can get this. Okay, so these can happen at different layers in the neural network, right? So I have one layer that deals with these root morphemes, and I change them up, and I get conjugates where I have several morphemes put together. So this is the slide that people see very often. Let me see what I can show this. So when I take a word and I represent it as a vector, which we'll talk about whoever's presenting next week, we get something like this, all right? So you may not be able to read it. Can you guys read it in the back? Not at all? Okay. So basically, there are some things down here that are words that are verbs. So be, being, been, they're all in this part of the vector space. So these means similar things. They're different inflections of the same word. Over here, I have need and help, two words here that have some type of semantically similar meaning. And then over here, we have a cluster of verbs that are other things, like come and go. They're directional verbs. They're actually in the vector space quite close to each other. Say, think, and expect, all in one cluster. Right? Take and get over here. Okay? So by using the word vector representation, if we take that vector representation, try to flatten it down using dimensionality reduction of some sort into a two-dimensional space, we can see they preserve some semantics, right? That words that have similar meaning, antonym, synonym, or different inflection, they are quite close together in the vector space. Any questions so far? Okay, so if you take traditional NLP, you learn about syntax. We have phrases in languages. So we say, just like we saw at the slide at the beginning, we would have a sentence right down here at the end. And you take pairs of words or groups of words together and you form them into a new, what they call constituent. Constituent is an internal node in the tree. So for example, here it says, the house at the end of the street is red. Right? So we know is red is the predicate, it's the verb, it ends the sentence. But this thing over here, all of it is a noun phrase, right? So there's actually a lot of noun phrases in the sentence, like the street is a noun phrase. It's composed of these two, determiner and noun. I put them together, right? And here I have a prepositional phrase of the street. End of the street is a noun phrase, right? So these are very discrete because we give them labels. Like we, one of the people here was asking earlier, do I have to classify them? Do I have to give names to them? In standard natural language processing, we would call these by specific names, right? A noun phrase, a verb phrase, or specialized categories of these, okay? But in deep learning, we don't need to do that, right? We said that we're going to try to learn a representation of the data rather than explicitly signal what that representation is by giving it a name, okay? So then every word and every phrase has the same form. It's basically just a vector, right? So we saw vectors lying flat just now. Now we have them oriented vertically, and we can just compose these together, right? A neural network can say, take from two different nodes that feed it and say, I want those inputs. I exclude the rest of the inputs as I don't want them. I exclude them. So then I'm going to build a representation at the second layer of what this NP is composed of just these two words, okay? So somehow I can do that. I can either average them together or something of this to compose a new representation, a new vector that represents that particular noun phrase. Okay? So what I'm trying to get at it here is that, you know, these labels, which we might normally call a sentence or a verb phrase or prepositional phrase, these are just labels for convenience for us. They're not actually in the neural network at all. Right? We are just propagating the information, letting the neural net figure out what pieces of information it wants to aggregate. Okay? Then let's go one level higher. So that was syntax, right? Building up the representation of the sentence, knowing what is the subject and the object. Let's go to semantics. So semantics here is traditionally thought of as lambda calculus. I said before, if I say the word I, computer trained in the traditional ways of natural language processing would use a form of lambda calculus. Lambda calculus is basically a way of keeping track of variables and assigning them to parts of the natural language utterance when they become available. So let me give you an example. It's just a little bit hard to understand. Let's take the word likes. Okay, this is a verb, right? Something likes something, right? I can say that's what this verb does. It associates a subject with an object, right? But at this point in time, when I hear the word likes, I don't know what is being liked, and I don't know what is doing the liking, okay? So lambda calculus allows me to represent that. I'm going to say that I have this predicate likes x, y. X is a variable, y is a variable, and I'm just going to keep them as variables just like we do in, you know, algebra, right? I'm going to assign the value later when I can figure it out, right? So for example, I see likes Sue. Oh, then I know what the direct object is, right? So when I use lambda calculus, I can combine these together and I can resolve what is being liked, right? This y here, likes xy, the y becomes associated with Sue, right? So this predicate up here is a verb phrase that carries the semantics of an action liking. I don't know who, but I know that what's being liked is Sue, okay? So this is the semantics of what this lambda calculus is doing. When I further get the noun phrase that represents the subject, well, then I can compose the whole thing. So you can think of a verb as some type of acceptor, right? It's got two receptacles for things that it can accept. And as I parse through the sentence and I join these attributes together, I know what is composed inside of it. Does that make sense? Okay. So this is how we structurally do it in traditional NLP. Now in deep learning, we're going to think about again, the same type of representation. We already said that words, phrases are all vector form, right? Some type of probability distribution, right? And for every one of these phrases, I'm going to have some type of logical expression also as a vector. Okay, so I have different layers of my social neural networks to do this, right? The softmax classifier to give an actual output, right? A comparison layer to do some of these other things to decide whether it's supposed to be this or supposed to be this. It comes out as the right answer for a particular representation. So at the bottom, I don't think you can read this, but it says all reptiles, some turtles, right? All reptiles walk, some turtles move. And I want to find out what this means at the end, right? So I compose all of these together, and I'll get out a semantic representation that's quite similar to this one. That knows that I can compose these to mean all reptiles, and then associate that with the verb walk here, and for this to be some type of comparison, right? Because when I say all reptiles walk, some turtles move, that implicitly is some type of comparison operation, right? If you think about it. Okay, sentiment analysis. We already had this slide, right? So the same type of deep learning model that can be used. This is one of the nice things about applying deep learning in natural language processing is that we can basically use the same simple model, right? Where we have a neural network, vector representation, right? And we use that model with different types of layers and operators, and we can get out something that can do sentiment analysis, can do morphological analysis, do semantic analysis, and syntax, using basically the same primitives, just different operations inside. Okay, so I think later on in at the end of the first session, around week 6 or week 7, we'll talk about recursive neural networks. Okay, and question answering. I think this is one of the other applications they said, right? So a lot of feature engineering was used to capture world and other knowledge. So for example, is the main verb this particular thing, trigger? So there's a lot of question answering that's done on news articles. So it said, did something trigger something else to happen, right? So then we have to think about, okay, if that's the case, then I can assign different roles to certain things in the sentence, right? Am I looking for an agent? Am I looking for a theme, right? And then say something about what are the conditions that it applies to that. So if it's not a trigger verb, then maybe some other conditions hold for that. Okay. So I guess you're hearing the same story over and over again. We can use the same model, and we can store the facts in vectors. Just like we compose all of the words as vectors, all the morphemes as vectors, we basically store a tuple that represents a fact as a vector, and we can store them in our knowledge space, right? In this high-dimensional space. So for example here, these are all the presidents, okay, of the US, located in here, right? And they've been put into this two-dimensional representation by the deep learning model to try to cluster them in some ways. So we have here George Washington, Thomas Jefferson, John Adams. These were the basic founders of the US. And in other places, I think in this particular diagram, it's not listed here. This is just for the American presidents, I think. But for some of the other ones, you can see that they've grouped prime ministers of the UK, explorers, and then emperors from Wikipedia. So this, I think all of this data was mined from Wikipedia. Okay, one of the holy grails in natural language processing is machine translation. Okay, the idea is that you can transform one human language to another. Okay, so this is what diagram that they call the machine translation swimming pool. It's a, if you look from afar, you can think, you're at this shallow part of the pool and you're looking way into the deep end. Okay, so at the front, there's direct translation, meaning that we have to figure out how to go from one language, let's say Chinese, and go directly to English using some complicated translation algorithm or routine or grammar. Okay, if you go farther and farther up this triangle, we get to deeper and deeper representations. So for example, we might think that even though we all speak different languages, somehow our neural nets, our organic neural nets are structured similarly. We capture language in the same parts of our brain. We have the same neural capacity to understand. So in natural language processing, we represent that as interlingual. This is the holy grail, where we can think about all of language as having some intermediate representation, which all of us humans share. Okay, if you know about linguistics, you've probably heard about Noam Chomsky and universal grammar. That's the idea. Okay? So the idea is to go not just from English to Chinese, because if we did that, then if we wanted to go from English to French, we would have to have another entirely separate version of translation. And then if I want to go to French to Spanish, again, an entirely separate set of translation routines, right? The Holy Grail is like, forget that. We're just going to take English, transform it to our intermediate representation, this universal language, and then translate it, decode it into Chinese, right? Take that semantic form and transform it into Chinese. Okay? So when we do deep learning, that's exactly what we do. We're trying to move up this region, right? Encode some semantic version, right? And then push it down this way. So there's, I think, Raphael and myself, we were both in Berlin a couple of weeks ago. We saw some of these technologies in practice. So Google has a system where they are able to translate from one language to another without having any example of these two languages with the same sentence. That means, for example, if I have a French sentence and a Spanish sentence that mean the same, usually I would have to get lots of pairs of these sentences and train the system to recognize the patterns that make French transformed into Spanish. Okay? What they were able to show is that you can get to French-Spanish translation by using French to English and Spanish to English, using only sentences of that sort. No sentences of Spanish to French at all. Okay? Just going through this intermediary, they were able to get translation accuracy that was quite improved from the current state of the art. Okay, so I illustrated that. Okay, so this is done in a lot of current systems now, where we have some sequence-to-sequence learning that's being figured out here. So here, for example, I have a sentence, A, B, and C, end of the sentence, and I want to figure out some information from it. So I might start with sentence here, output the sentence here. So these are input layers. They're propagated out. And try to learn representation for A, B, and C with respect to a different encoding. So for example, these might be words, and then I want to map the part of speeches to them. Okay? So the source sentence is mapped to a vector, then the output sentence is generated. So again, this could be, you know, I ate lunch, and this could be, you know, NP, VP, NP, something like that. Or it could be, you know, I ate lunch and equivalent in Japanese. Okay, so this is all different types of sequence-to-sequence translation or decoding, right? Where I map one input representation and I transform it to a different input output representation. Okay, so Socher works for MetaMind that was acquired by Google, so you can run their system. You give them some type of input, natural language, and you can ask a question and run the DeepMind system to get an answer for it. Okay. So I think that's more or less everything. This is the last slide that I'm going to cover today. Okay. So next week's lecture, hopefully we're going to cover learning vector representations for words and what they actually represent. So the teaser for this is something like this diagram. I don't think you can see it, so let me just tell you what's going on here. Okay, there are some lines here that connect two different words. And these words are different with respect to one dimension. Okay, male versus female. So this is brother and sister. This is nephew and niece. This is uncle and aunt. This is man and woman. Even this one is king and queen. Okay, so what we're basically saying is if you start with this vector, and you subtract away this vector, whatever that means, okay, we're going to end up with this word. And pretty much all the vectors are aligned in typically around the same way and same distance. What does this vector then mean? It means subtract maleness, add femaleness, right? Okay, so that's one of the wonders of deep learning right now, is that this input representation is being learned by the network, right? That it can figure out that there is such a pattern, and it's going to accord that pattern of minus maleness plus femaleness with a vector length that you can apply to any word. So you know, there's quite an interesting set of word analogy tools that you can run using words_vec after you finish that lecture, where you can type in any word, then try to subtract this vector and get another vector. So maybe like taking, for example, Rio de Janeiro and subtracting male and female, adding femaleness, you'll get another country that has more news about females. Okay, so that's just an example of things that we can look forward to next lecture. Okay, so it is 7:30 now, so I'm going to end the lecture there. It's very hot in here, right? But the important thing is we need to know who wants to present for next week. So I'm going to spend a couple minutes looking at this sheet. Okay. So I need you all to fill in some days, some topics that you're interested in. So we have one person for week 4, but no one yet for week 3. Okay. So if you, there's one person who's nicely volunteered for that. Okay. Please don't change your thing so we have something to present. So what I'd like to do is have you all try to fill in one of these cells. Okay, if you're going to participate, and I will try to arbitrate. If I think there's not enough people for one particular group, then I will assign some of you to others. So I'll do some load balancing for that. Okay, now of course you guys are practitioners or you're students. You probably don't know the material as well as I do. In fact, I don't know the material well at all. This is why I proposed it in the first place. The best way to learn about something is to attempt to teach it, right? Yes? So we're all fair game here, okay? I did the first batch. I sort of know what this material is, so I'm presenting it today. But I hope you will join me in this journey, and we'll work together to try to do this, okay? So thanks for coming. I hope it was worth your time. I don't want you to go quite yet, okay? I would like you guys to stay around, and basically, if you are with colleagues, what I would suggest you do is we're going to take turns introducing ourselves, just for 1 minute per group, okay? So we can get out of here at a reasonable time, all right? And I just want you to say a little bit about what interests you in this course, whether there's some particular reasons or applications that you're going to do for that. So let's start with this side over here. So if you don't mind, could you just stand up, state your name, and if you have colleagues here, ask them to stand up and then tell me, tell the whole group about what you do or some problem. So, Miss over here in the black shirt and glasses. Okay. Okay. Who are you affiliated with? Some lab. Okay. All right. So the next person, Miss.
I'm Zhiling. I'm from NCS. I'm currently working at engineering. I think all my colleagues built today.
Okay.
So the only one here. I'm interested in this because while working at NLP, it's clear that there are a lot of applications of deep NLP that can be applied to the massive data set that all the government agencies have, especially those like NLP. So there might be very good applications for this.
With MHA, did you say? Okay. Excellent, thank you. Sir?
I'm David. I'm from DSO. The people from my lab are not here because they forgot yesterday. Why I'm here is I want to learn more about the theoretical stuff about deep learning. Because you always hear about applications, but it's hard for you to find a resource to learn the actual math. Thank you.
Okay, sir.
Hi, my name is Richard Socher. I'm a student, part-time student of Master of Science in Business Analytics. It's a British company over there, which studies a joint course between the School of Computing and Business School. And I'm working in daytime. I'm working at hedge fund, investing money in Japan equity. So my area of interest is in especially the sentiment analytics, like the program which can read endless reports from a newspaper and extract the useful information or judge the sentence. The content is positive there. That's it.
Great. Thank you. Sir?
Hi everyone, my name is Richard Socher. I am currently working in a company called Lattice, which is based in the semantic web. So this is my colleague.
Myself, Ashutosh Gaur. So we both are working in a Lattice, and the main objective to attend this class just to understand the possibilities of deep learning, so that we can get some the accuracy. Especially right now, actually we are looking for a kind of our personal project. It's not the official one, but
Not yet.
yeah. So we are just looking how to classify the official communication in some organization. In case day to day we are getting so many communications, so we can develop a kind of engine so that that particular system can easily classify all those communication in different categories. So for that thing, actually, we are coming here to if we can use some deep learning algorithms so that we can accurately classify those things.
Okay.
That was the basic motive.
Great. Thank you. Okay, over there in the black shirt.
I'm a NUS law student by the Department of AI, and I'm from the legal hackers project. So, deep learning is highly important.
Sir?
Yeah. My name is Edward. I'm actually a student from NLP CS. So I'm working on my final year project on deep learning for speech recognition. As I think this is quite useful.
Great. Sir?
Hi, I'm Nicholas. I'm a student for part of this course. I did my master's in the relevant field, and I worked at HP as a data scientist for a while before I continued for my PhD. Nice to meet you.
Thank you.
Hello everyone, my name is Socher, and I'm officially registered this class. I'm from SOC. I just finished my undergraduate study in science, and now I'm a PhD student. Nice to meet you.
Thank you. Sir?
Hi, I'm Yongjiet from NTU School of Computer Science, and I'm working as a software engineer in ENW at NTU.
Okay.
Hello, my name is Rafael from Esperar, with my colleagues Luis and Sunil. We are from the Human Language Technology in Esperar. Sunil works with speech recognition. Luis and I work on dialogue technology and question answering. Sunil has already some experience working with deep learning in speech recognition, and we are starting to use this technology also for training models for dialogue and question.
Thank you, all three. Sir?
Hi, my name is Terence. I'm from DSO. So back in DSO, I work in various areas of our projects. One area is in NLP, where we process some classified information for information retrieval. It's classified. So, but and another area is also, it is in the areas of cybersecurity, where we do malicious behaviors detection. Yes, so that one I'm looking to see if how RNN can be applied to build models of the cyber systems.
Okay, great. Thank you. Miss?
I'm Fu, and I'm from A-Star, and my work is currently concerned with information retrieval and natural language processing, so I want to know more about natural language processing on this course.
Okay, thank you. Sir?
So I'm Snow. I come from NUS Center. I was studying about computer vision, so I know want to learn something about the NLP and the deep learning. Nice to meet you.
Okay. Yes.
Hi everyone. I'm Jonna. I'm a research assistant from the NUS Center, and my recent research interest is video representation learning with deep learning. So I'm also interested in the video application with NLP, like user comments.
Comment analysis, sir, Anish.
Hi, I'm a PhD student at med school. Previously, I was working in speech recognition using deep learning. So I have some experience with speech recognition using deep learning, and now I'm working same using deep learning techniques into text, basically digital learning, which is academic text, but in large volume.
Shana.
Good afternoon, everyone. I'm Xiangnan. Means former PhD student, and I'm now working as a postdoc at the NASA Research Center. My current research is about using the nets for the recommendation system. So there are already some works on it, but they mainly use the deep learning technology for modeling the side information. For example, the text, the image, and the video. These features, but they did not touch the core part of the recommendation system, which is the interaction between the users and items. So this is the research direction I'm currently working on. So I attend this course to want to learn more technical stuff.
Tao.
Hi, I'm Tao. I finished my PhD this year. I'm now a postdoc in NUS. So my PhD work is about image trees analysis and modeling and representation. Since I study both the image and the text, I'm also interested in applying learning to my research topic.
Hi everyone, I'm Chen Fang, and I'm the final year postgraduate student of me. And my research is automatic motivation for IPS forum. That is to predict whether a post is correct or not in a structured forum. And I hope deep learning can help in my research.
Yes.
Hello guys, I'm Chandana. I'm doing my master's in business analytics. We had a course as part of the course as computational intelligence, but that was like basics of neural networks. I'm here to have a better understanding of neural networks and its applications.
Great.
Hi everyone, I'm Joel. I'm currently still serving national service in the army. Yeah, so I'm not really working on anything. Yeah, I graduated from NUS High School 1-2 years back. Yeah, and I'm just here to get ready for university next year and just play around with your neural network because I had a bit of exposure in high school. Yeah, working on project.
Great. Okay, great.
Alex, I'm a NUS student from SOC, and I'm here because I want to learn more about deep learning. Because my final year project is related to deep learning, which is the application of deep learning program analysis.
Hi, my name is Juan. I'm from ITs. Chandana is my friend. Yeah, so I'm here for to learn about deep learning. Not so much on NLP, but applications in images also.
Thank you.
In Mandarin, I work in advertising. We strategy work. I just curious. Let's review it.
Great. Glad to have you. Thank you. Sir?
Actually, right now working in the data analytics in CS.
I didn't look at my other colleagues here. I was a real improvement officers. So yeah, but my other colleague couldn't come because he was not. So I think this course is mainly for my own.
Great, thank you.
My name is Sem I AY, and I'm a research fellow in SICS, Institute of Digital Science. Yeah, I'm not really related to my work, but then I'm trying to get in touch with the state of the art in machine learning. It's one of my most interest in, I have the most interest in machine learning.
Great.
So, I'm currently doing masters in business analytics. So we have an elective in Texas coming next month. So part of it, I'd like to understand more about it.
Oh, good.
I also have my colleague.
Okay, so you're skipped. Yeah, your friend did it for you. So, Tani?
My current research interest is politics system, and I'm very interested in it. Works very well for large government, so I'm curious to learn.
Okay, great. Manpreet?
Hello everyone, I'm Manpreet and I'm an intern at Mayland. Currently I'm working on using deep learning for sequence-related tasks, and there's a slide that was on sequence-related tasks. That's my current task. It's a part of a larger digital scholar library work. And I'm interested, I'm really excited about this course because we all get to learn together. And I hope to be able to do those projects and programming assignments that Sir mentioned. So we can form a group on Slack, and if anybody's interested in delving into programming assignments, then
Awesome, great. Yes.
I'm Kibram. I'm from Python.
Okay, so you guys are all skipped. Who's the ringmaster? Okay.
We have applications in text mining, as they mentioned in two comments.
Right.
So image processing, also in vapor quality predictions.
Actually, our current application is quite diverse. We have a lot of different areas, from graph analysis, like traditional machine learning, like both supervised learning or non-supervised learning. We do a lot of regression analysis, classification, clustering, and even we have a few data visualization projects. So because as Ebony mentioned now, because we have a lot of tool logs, our technician will text in a lot of comments on each maintenance. So we're trying to evaluate the capability of deep learning to combine the text data with our traditional numerical or categorical data together, so we can develop better predictive models. So that's our purpose.
Wow, we can hold a class at your site, given how many people you have. So yeah, I hope you guys can all help to participate, take turns in presenting the work. So sir, over here.
Yeah, hi, I'm Shubham. I'm a student from India. I'm working at SUDD with Delhi. And Professor Dr. Lu Wei is guiding us. Yeah, so we're working on a lot of different NLP projects.
Okay, great. Sushan?
My name is Socher. I'm a graduate student here. Here my friend is sesssion analysis. And this course is pretty
Joey?
Hi, I'm Joey. I'm an undergrad from computer science, and I'm here just because I'm to learn more.
Sir?
I'm Sean, and I'm year 2 undergraduate from SOC. And I'm also doing intern in my course. I come here is want to experience the level 6 modules, and hope I can learn something from this module, and hope I can learn something from you guys.
Okay. I will tell you, level 6 is not that different from level 2, actually. I used to think, you know, as a student in undergraduate, those level 6 courses must be killer, but it's just a natural progression. So it's not any harder. It's just that there may be a little bit more prerequisites. So if you get lost, don't worry. If you get the concept, that's fine. Yeah, Kaz?
I'm a senior researcher in Queen's Group. My research topic is recommendation system. I'm very interested how to apply
Okay, Mutu?
Hi, my name is Mutu. I'm a PhD student. I work with Min. We gave a list of these are about my research. It's a book discussion forums. So one of the main interests for me in deep learning is LSTMs. I would like to use LSTMs to capture the form structure. I will see if that's useful.
Okay, sir in the front?
I'm from Micron, and I actually have a question. Why represent as vectors? I'm sorry if you covered it or
No, I didn't cover it, so that's a very good question. So can you continue?
or tensors, why does it not fit them? I think two-dimensional vectors?
So I think you can represent it. I think the current technology previous is that we just use scalars. So that was a big problem. So when we go over next week's lecture, we talk about word representation as a vector form. And we change from a one-hot representation to a distributed representation. You'll see a lot more power of that. To say whether it scales up to a two-dimensional array or a three-dimensional tensor, that's still to be remained. I think if there are good arguments to go in that representation for representation, it might work. It's just that I think currently what we can handle computationally is probably a vector form, right? We've been using scalars for most of these things for a long time, and moving to a vector representation gives us added power to harness a lot more data and use them latently. So pardon me if that's not a very precise answer. I think hopefully it'll be on the onus of the people who present week 3 to show you why the vector representation is a good representation. Okay, but the short of it is that the scalar is just too small. It can only represent one value. The vector form can encode a lot more distributional information. So for example, a single word is not defined as the word, but by the company of the words that it keeps around it. So if you can remember all of the words that are to the right of a particular word, like doctor is usually found with nurses, usually found near hospitals and things like that. I mean, in a sentence, for example, then you can know more about what doctor means because of the neighbors that you can see it with. So all of that is encoded in this vector format, where we encode more about what words co-occur with a target word, and we define the meaning of a word by its representation of you know, the other words that we typically see with that word. Okay.
So basically, you initialize the first, for example, the king and queen.
Yeah.
Does the algorithm dynamically arrive on a vector for a given word?
Yes.
Or do you provide the vector from the random vector?
You usually start with a random vector, and then you apply some training algorithm, iterative training, to have the vectors match the data. So after some number of stochastic iterations, you'll converge on well, hopefully the convergence comes together. You have vectors that seem to represent the same thing, where each dimension has some semantic meaning. But exactly what meaning that particular dimension is not usually very clear.
If you add another dimension, you can get the context information.
Yeah, so that's what some of these layers are doing, right? The layers in the deep neural network, that's why they call it deep, is to compose a lot of these things together. Like in a lot of the slides where you saw something being drawn together and some other thing coming out of that, like a phrase or meaning, is all of this composition that's being learned through the composition of the neural net, right? So you start with a very basic, primitive representation, which is the word vector, or the phoneme vector or whatever, and then you compose them successively through the layers until you get the type of application you want at the top. So that's the general architecture of that. Yeah. Okay. Great. So over to back there. So Piers.
I'm Piers. I'm an undergrad, and I've been working with some NLP tools. So I've worked with traditional NLP tools and some powered by deep learning, and I found that there's a stark difference in accuracy and power. And so I was just really intrigued. And I just
Connie?
I work with neural networks and often learn the inclusion of networks and facial recognition. So I want to learn more about RNN and
Okay. Did we cover everyone else from Micron? Yes? You guys are like, yeah, I don't want to talk. Okay. Then Terrence, you're the last.
Hi everyone, my name is Terrence. I'm an associate professor here at School of Office, Practice and Data. My main area is actually computer vision, images and all that. Within that, I do more facial analysis. The reason I'm here is that I'm actually very late. One slide, the main show is that for the past 2 years, computer vision people have been deep learning, and I'm playing catch up. Right? I was at a computer vision conference, one of the big ones in Las Vegas last month. 80% of everything is deep. And the deepest deep now is over 1,000 layers. Over 1,000 layers. It's called visual learning by the folks at NSRA, and it's Microsoft Research AG. So they've come up with a 3-layer thing that can replicate and scale up to over 1,000. Surprisingly, it doesn't do better than a 200 layer. Still 200 is phenomenal. So I guess I'm here because I have no choice. I have to figure out what this is all about, what the fuss is. As it is, I'm 2 years late, so I'm just a newbie as everyone here. So I'm going to ask some questions. I'm glad to be here.
So I'm glad you said you would ask them questions, because I'm also playing catch up. The reason why I'm offering this course is because I also don't know deep learning. So a lot of the students are ahead of me in that respect. So that's why we're offering it. That's why we decided to open it up to the public. So I hope you will join us in our course to, as I said, level up the whole community. It doesn't matter whether you're undergraduate or even pre-undergraduate, that's fine. Or you're like me and a dinosaur and still try to survive extinction, that's also fine. We're gonna all try to do this course together, all right? So with that, we'll end this course. It's almost 8, so I think everyone wants to go home, right? Thank you for joining. So next week we'll be here at the same time with different people. Thank you.